So we'll finish this section off with a discussion of infinite limits. And for our purposes, what they're going to do is provide us with a way to use limit notation to describe the behavior of a function near its vertical asymptotes. So here you can see I've drawn a graph of a function f. We don't know the exact rule that defines f, but we at least have a graph of it, at least for some portion of x values. And we can see that there's a few vertical asymptotes. So basically my goal here is just to show you how you can use limit notation to describe the behavior of the function near the asymptotes. So this is what you would typically write in this case. So if I write the limit as x approaches -2 of f of x, and let me say from the left there, so we're talking about the limit as x approaches -2 from the left of the function f of x, let's try to assign a sensible value here. So as x gets closer and closer to -2 from the left, do the standard thing where you take the path on the curve. Right, the corresponding path on the curve, that would be this one, right? And usually you'd ask the question, you'd say, is this path approaching a point? And the answer is no, it's not really approaching a point. It's just exploding in the upward direction. And the closer you get to -2, the steeper this curve is and the faster it's growing. So it's not approaching a point. So we're not going to be able to assign a real number to this limit and make any sense of it that way. But we can still use this limit notion to describe the behavior. Right? Because if it's exploding upward in the direction, and there's no, put it this way, any positive number you ever come up with, the height of this function will eventually go far beyond that. Right? No matter how large of a number you pick and you mark it off on the y-axis, it's not going to work as a barrier. This curve is eventually going to punch through it and go way higher. So there is no finite number that would make sense to put here. So we can either say it doesn't exist, but that's almost like a wasted opportunity to give some information here, because we might as well just say infinity, because what that's doing is it's telling whoever's reading this, it's saying that as the x values get closer and closer to -2, the y values of the points on the function explode in the upward direction and they get arbitrarily large. That's what this notation really means. That's what's packed into here. But just think of this picture, right? If you have a vertical asymptote and the function blows upward, you can just use this notation to describe its behavior. And since if I take the values of x close to -2 from the right, same thing happens, right? As x gets close to -2 from the right, the values of the function just explode in the upward direction. So we could also write the limit as x approaches -2 from the right of f of x is equal to infinity. So if the two one-sided limits are written this way, we might as well just use the same notation for the two-sided limit, right? As x gets close to -2 on either side, the function explodes upwards on either side, right? So let's just say the limit as x approaches -2 without specifying a direction. So in other words, the two-sided limit, we'll say that that's equal to infinity also. Okay, let's do a little bit more. Let's deal with the other asymptotes as well, just for practice. So if I take the limit as x approaches 1 from the left of f of x, well, what's happening? Well, as x gets closer and closer to 1 from the left, what are the y values doing? The y values of the points on the curve are going upwards, and they're just exploding upwards, right, and going off. You can think of this as going off to infinity, as if infinity is a place that you can go, when it really isn't. But that's a pretty good way to describe it, right? The curve just goes off to infinity in the positive direction. So we might as well just write infinity, just like we did with this asymptote on either direction. But what about the limit as x approaches 1 from the right? Well, as x gets closer and closer and closer to 1 from the right, well, the y values are doing the opposite, right? They're exploding, but they're going in the downward direction, or the negative direction. So we just use the same strategy, but we'll just say negative infinity to imply that we still have the explosive behavior, but it's in the other direction. It's going downward in the negative direction. Okay, so unlike the previous case where the two one-sided limits were both going to the same place, in this case, the limit from the left is infinity, and the limit from the right is negative infinity. So if these don't agree, we go with the normal convention and we say that the two-sided limit does not exist. So if I say just the limit as x approaches 1 of f of x, I would say that does not exist. I almost fell into the trap of writing an equal sign. It's just a habit. But this is what you would say. This limit does not exist. And it comes down to the fact that the two one-sided limits don't agree. And if they don't agree, the two-sided limit can't exist. Okay, let's do one more example. There's another vertical asymptote at x equals 5. Let's describe it. So the limit as x goes to 5 from the left, let's say, of f of x. Well, as we get closer and closer to 5 from the left, the corresponding path on the curve, its y values are exploding in the downward direction, so we'll just say that this is equal to negative infinity. And the limit as x approaches 5 from the right, well, as x gets close to 5 from the right, same thing's happening. The curve is aimed in the downward direction, so the y values, as x gets closer and closer to 5 from the right, the y values are just exploding in the downward direction, so we'll say negative infinity. So in this case, both of the one-sided limits were negative infinity. So, well, it makes sense to just say now that the limit as x approaches 5 of f of x is equal to negative infinity. Okay, so that's the last thing I want to mention in this section. In the next section, we'll talk about how to calculate limits in a more robust way that works in a more variety of cases where you don't have the graph available necessarily, and you certainly won't be wanting to do tables of values. Okay, so that wraps up this section.